Yes, an induction problem can occur when electrical conduits run parallel, especially if grounding and bonding are not properly addressed. This issue stems from electromagnetic interference, often abbreviated EMI, which can disrupt the functionality of sensitive electronic systems such as addressable fire alarm systems. When electrical current traverses a conductor, it generates a magnetic field surrounding that conductor. Should another conductor be situated in close proximity, the magnetic field emanating from the first conductor can induce a current within the second. This phenomenon is known as electromagnetic induction. In the context of a 277 volts lighting conduit, a substantial current flow is likely, resulting in a significant magnetic field around the conduit. This magnetic field, in turn, can induce a current in the adjacent addressable fire alarm system conduit, potentially causing malfunctions or false alarms within the fire alarm system. To effectively mitigate this issue, a multifaceted approach is recommended. Firstly, ensure that all electrical conduits are meticulously grounded and bonded in accordance with relevant electrical codes and standards. Grounding provides a path for fault currents to safely return to the source, while bonding ensures that all metallic parts of the electrical system are at the same electrical potential. This minimizes the potential for voltage differences that can drive stray currents and exacerbate EMI. Secondly, proper grounding and bonding minimize the generation of EMI. This practice safeguards electronic devices from potential damage caused by electrical disturbances. Thirdly, consider implementing shielded cables for the fire alarm system wiring. Shielded cables incorporate a conductive layer, typically metallic, that surrounds the inner conductors. This shield acts as a barrier, attenuating the ingress and egress of EMI. By reducing the amount of interference, shielded cables provide an extra layer of protection for the fire alarm system, enhancing its reliability and resilience against electrical noise. Supplementing the above measures, additional considerations can further optimize the electrical system's performance and minimize the risk of induction-related problems. One is conduit separation. Maintain adequate physical separation between the 277 volts lighting conduit and the fire alarm system conduit. The greater the distance between the conduits, the weaker the induced current will be. Refer to applicable electrical codes and standards for specific separation requirements. 2 is conduit material. While polyvinyl chloride, abbreviated PVC, conduit is commonly used, consider using metallic conduit for at least one of the circuits, particularly the 277 volts lighting circuit. Metallic conduit provides inherent shielding against EMI. 3 is grounding electrode system. Ensure that the electrical system has a robust grounding electrode system. This system typically consists of ground rods, ground plates, or connections to the building's metal frame, all interconnected to provide a low impedance path to earth. A well-designed grounding electrode system is essential for effective grounding and bonding. 4 is surge protection. Install surge protective devices, abbreviated SPD, at the main electrical panel and at critical points within the fire alarm system. SPD help to divert transient voltage surges, such as those caused by lightning strikes or switching events, away from sensitive electronic equipment. 5 is regular inspections. Conduct regular inspections of the electrical system to verify the integrity of grounding and bonding connections. Look for signs of corrosion, loose connections, or damaged components. Address any issues promptly to maintain the system's effectiveness. 6 is professional consultation. If you continue to experience problems with the fire alarm system, consult with a qualified electrician or electrical engineer. They can perform a thorough assessment of the electrical system, identify potential sources of EMI, and recommend appropriate solutions. 7 is cable routing. Route cables carefully, avoiding sharp bends and keeping them away from sources of EMI such as motors, transformers, and electronic equipment. 8 is filter implementation. Incorporate filters into the power supply lines of the fire alarm system to attenuate unwanted electrical noise. These filters help to block high-frequency interference that can disrupt the system's operation. 9 is testing and certification. After implementing any changes to the electrical system, thoroughly test the fire alarm system to ensure that it is functioning correctly. Obtains certification from a qualified testing agency to verify compliance with applicable codes and standards. 10 is documentation. Maintain detailed records of all electrical work performed, including grounding and bonding connections, cable routing, and equipment specifications. This documentation will be valuable for future troubleshooting and maintenance. Induction problems in parallel electrical conduits can be a complex issue, but by implementing the aforementioned measures, you can significantly reduce the risk of EMI and ensure the reliable operation of sensitive electronic systems like fire alarm systems. Remember to prioritize safety and consult with qualified professionals when working with electrical systems. It is important to understand the underlying principles of electromagnetic induction to effectively address this type of issue. Induction occurs when a changing magnetic field induces a voltage in a nearby conductor. The strength of the induced voltage depends on several factors, including the strength of the magnetic field, the distance between the conductors, and the orientation of the conductors. In the case of parallel electrical conduits, the magnetic field produced by the current flowing in the 277 volts lighting conduit can induce a voltage in the fire alarm system conduit. This induced voltage can then interfere with the operation of the fire alarm system. The severity of the interference depends on the magnitude of the induced voltage and the sensitivity of the fire alarm system. Some fire alarm systems are more susceptible to EMI than others. To minimize the effects of induction, it is essential to reduce the strength of the magnetic field and the coupling between the conduits. Grounding and bonding play a crucial role in achieving this. Grounding provides a low impedance path for fault currents, which helps to reduce the voltage potential between the conduits. Bonding ensures that all metallic parts of the electrical system are at the same potential, which minimizes the flow of current between them. Shielded cables also help to reduce the coupling between the conduits by blocking the electromagnetic field. In addition to these measures, it is important to follow good wiring practices. This includes using properly sized conductors, avoiding sharp bends in the conduit, and keeping the conduits as far apart as possible. Regular inspections and maintenance are also essential to ensure that the electrical system is functioning correctly and that there are no loose connections or damaged components. Addressing induction problems in parallel electrical conduits requires a comprehensive approach that includes grounding, bonding, shielded cables, good wiring practices, and regular maintenance. By taking these steps, you can minimize the risk of EMI and ensure the reliable operation of sensitive electronic systems. The National Electrical Code, abbreviated NEC, provides specific requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety and proper functioning of electrical equipment. Article 250.4 of the NEC specifies the general requirements for grounding and bonding. It states that all electrical systems must be grounded in a manner that prevents voltage from exceeding specified limits. Article 250.92 of the NEC covers the bonding of metal enclosures. It requires that all metal enclosures containing electrical conductors be bonded together to form a continuous electrical path. Article 300.3 of the NEC addresses the installation of conductors in parallel. It states that conductors in parallel must be of the same material, have the same cross-sectional area, and be installed in the same raceway. Article 310.15 of the NEC provides guidelines for determining the ampacity of conductors. It takes into account factors such as the conductor size, insulation type, and ambient temperature. Table 310.16 of the NEC lists the allowable ampacities of insulated conductors rated up to 600 volts. Article 517 of the NEC covers the installation of electrical systems in healthcare facilities. It includes special requirements for grounding and bonding to minimize the risk of electrical shock to patients and staff. Article 760 of the NEC addresses the installation of fire alarm systems. It includes requirements for wiring methods, grounding, and circuit protection. When installing electrical systems, it is important to follow all applicable requirements of the NEC. Failure to do so can result in electrical hazards, equipment damage, and code violations. Consulting with a qualified electrician or electrical engineer can help ensure that the electrical system is installed correctly and safely. They can provide guidance on grounding, bonding, wiring methods, and other aspects of electrical system design and installation. Regularly inspecting and maintaining the electrical system is also essential to ensure its continued safety and reliability. This includes checking grounding and bonding connections, inspecting wiring for damage, and testing circuit breakers and other protective devices. By following these steps, you can minimize the risk of electrical hazards and ensure the proper functioning of electrical equipment. The specific grounding and bonding requirements for electrical systems vary depending on the voltage, type of equipment, and location. It is important to consult the NEC and other applicable standards to determine the appropriate requirements for a particular installation. In general, grounding electrodes must be installed as close as practicable to the service entrance and must be connected to the grounding busbar in the electrical panel. Bonding conductors must be sized appropriately for the size of the conductors they are bonding and must be installed in a manner that minimizes impedance. Shielded cables must be properly grounded to ensure that the shield is effective in blocking electromagnetic interference. Grounding and bonding are essential for the safety and proper functioning of electrical systems. By following the requirements of the NEC and other applicable standards, you can minimize the risk of electrical hazards and ensure the reliable operation of electrical equipment. There are several types of grounding electrodes that can be used for electrical systems. The most common types include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically made of copper or galvanized steel and are driven into the ground. Ground plates are typically made of copper and are buried in the ground. Concrete encased electrodes are typically made of copper and are encased in concrete. The choice of grounding electrode depends on the soil conditions, the size of the electrical system, and other factors. It is important to select a grounding electrode that is suitable for the particular installation. Bonding conductors are typically made of copper or aluminum and are sized according to the size of the conductors they are bonding. The NEC provides tables that specify the minimum size of bonding conductors for different conductor sizes. Bonding conductors must be installed in a manner that minimizes impedance. This can be achieved by using short, direct bonding paths and by avoiding sharp bends in the bonding conductors. Shielded cables are available in a variety of types and configurations. The type of shielded cable that is appropriate for a particular application depends on the frequency of the electromagnetic interference, the level of shielding required, and other factors. Shielded cables must be properly grounded to ensure that the shield is effective in blocking electromagnetic interference. The grounding connection should be made as close as possible to the point where the shielded cable enters the equipment. Electrical systems should be inspected and tested regularly to ensure that they are functioning correctly and that there are no electrical hazards. Inspections should include checking grounding and bonding connections, inspecting wiring for damage, and testing circuit breakers and other protective devices. Testing should include measuring the impedance of the grounding system and verifying the effectiveness of shielded cables. Regular maintenance is also essential to ensure the continued safety and reliability of electrical systems. This includes tightening loose connections, replacing damaged wiring, and cleaning electrical equipment. By following these steps, you can minimize the risk of electrical hazards and ensure the proper functioning of electrical equipment. Additionally, there are other potential sources of interference that could be impacting the fire alarm system. It is important to consider these factors during troubleshooting. One is electrical noise from nearby equipment. Certain types of equipment, such as motors, generators, and variable frequency drives, can generate significant electrical noise that can interfere with the operation of electronic systems. 2 is radio frequency interference, abbreviated RFI. Radio transmitters, cell phones, and other wireless devices can emit radio frequency signals that can interfere with electronic systems. 3 is electromagnetic pulses, abbreviated EMP. Electromagnetic pulses, such as those caused by lightning strikes or nuclear detonations, can generate high-voltage surges that can damage electronic equipment. 4 is poor grounding practices. Inadequate grounding can lead to ground loops and other electrical problems that can interfere with the operation of electronic systems. 5 is damaged wiring. Damaged or corroded wiring can create resistance and voltage drops that can impact the performance of electronic systems. 6 is loose connections. Loose connections can cause intermittent problems and can also generate electrical noise. 7 is improper installation. Improperly installed equipment can be more susceptible to interference. To mitigate these potential sources of interference, it is important to implement the following measures. 1 is install surge suppressors. Surge suppressors can help protect electronic equipment from voltage spikes and surges. 2 is use shielded cables. Shielded cables can help block electromagnetic interference. 3 is ground equipment properly. Proper grounding is essential for minimizing electrical noise and preventing ground loops. 4 is separate sensitive equipment. Keep sensitive electronic equipment away from sources of electrical noise. 5 is use filters. Filters can help block unwanted frequencies. 6 is inspect wiring regularly. Inspect wiring for damage and corrosion. 7 is tighten loose connections. Tighten loose connections to prevent intermittent problems. 8 is follow proper installation practices. Follow proper installation practices to ensure that equipment is installed correctly and is not susceptible to interference. Electromagnetic compatibility, abbreviated EMC, is the ability of electronic equipment to function correctly in its intended electromagnetic environment without causing interference to other equipment. EMC is an important consideration in the design and installation of electronic systems. There are several standards that address EMC, including IEC 61000 and CISPR 22. These standards specify the requirements for electromagnetic emissions and immunity. Electromagnetic emissions are the electromagnetic energy that is radiated or conducted by electronic equipment. Electromagnetic immunity is the ability of electronic equipment to withstand electromagnetic interference. To ensure EMC, electronic equipment must be designed to minimize electromagnetic emissions and to be immune to electromagnetic interference. This can be achieved by using shielded enclosures, filters, and other EMC techniques. In addition to designing equipment for EMC, it is also important to install equipment correctly and to follow good wiring practices. This includes grounding equipment properly, separating sensitive equipment from sources of electrical noise, and using shielded cables. By following these steps, you can minimize the risk of electromagnetic interference and ensure that electronic equipment functions correctly in its intended electromagnetic environment.